Let's now look at a simple derivation of time-independent Schrödinger's equation for a single particle. I want to emphasize from the beginning that this is a motivational derivation because Schrödinger's equation is a basic postulate of quantum mechanics. It cannot be derived from other basic principles of physics, just as Newton's second law of motion is the fundamental equation of Newtonian mechanics, and it was not derived from any other principles. Still, I think it may be helpful to provide a simple derivation of the time-independent Schrödinger's equation for a single particle, all based on the time harmonic wave function, the time-independent wave equation, and the de Broglie hypothesis. So the purpose is to show you why the equation has the form it does and why it naturally connects wave ideas with particle energy. We begin by assuming that the particle can be described by a wave function with harmonic time dependence, which is e to the minus I omega t. In other words, we write the wave function in the separable form as shown here. This means that the full wave function, capital psi of r and t, has a spatial part, psi of r, and a purely oscillatory time-dependent factor, e to the minus I omega t. This form is very common in physics whenever we are dealing with time harmonic waves or stationary states, as we will see later. Now, if the particle behaves like a wave, then the spatial part should satisfy a wave-type equation. For a time harmonic wave, the spatial part satisfies the Helmholtz equation as shown, where lambda represents the wavelength of the wave. So far, this is a standard wave description. The key quantum step now is to connect the wavelength to the particle's momentum. According to de Broglie hypothesis, we know that lambda equals the Planck constant divided by the momentum. This is one of the landmark ideas in early quantum theory. It tells us that matter has wave-like behavior with wavelength inversely proportional to momentum. So a particle with larger momentum has a shorter wavelength. So if we substitute lambda equals h divided by p into the wave equation here, we obtain the expression shown here. Since h bar or h slash equals h, the Planck constant, divided by 2 pi, and it is called the reduced Planck constant, the equation shown here can be rewritten in a more compact form as shown. At this point, the equation still contains the classical momentum p. So the next step is to express the momentum in terms of the particle's energy. For a single then relativistic particle of mass m moving in a potential f of r, the total energy is written as shown in this expression. We know that the first term on the right-hand side represents the kinetic energy, which is p squared divided by 2m, where m is the rest mass of the particle. And the second term, as we already mentioned, it is the potential energy. Rearranging this expression, we obtain the expression for p squared as shown. Now we insert this expression for p squared into the equation shown here. We obtain the last equation shown on the bottom of this page. This is already very close to the standard time-independent Schrödinger equation. Let me pause here and point out what has happened conceptually. We began from a wave equation, introduced the matter wave concept through de Broglie hypothesis, and then combined it with the classical energy expression for a particle in a potential. So this equation is really the result of marrying three ideas together: wave behavior, particle momentum, and energy conservation. In the next slide, we will rewrite this equation into the form you will see most often in textbooks and applications. Continuing from the previous slide, we obtained the equation shown here. It can be further rearranged into the standard form as shown. This is the time-independent Schrödinger equation for a single particle in a potential V of r. This equation is one of the most important equations in all of modern physics. It was first announced by Erwin Schrödinger in 1926, and it became a cornerstone of quantum mechanics.